The world of matrices is much broader with wide variety of applications. But what we are more focusing on is what is more required for our exam standpoint. Now, first thing that we need to understand is what is a matrix. Any array of numbers, for example, probably typically people represent matrix like this: 1, 2, some numbers. Any array of numbers represented in the form of rows and columns is what is called as a matrix. And typically these are called the rows. So in this matrix we have 3 rows, and the vertical ones are called the columns. So we have 2 columns in this example. So the matrix is typically represented as number of rows into number of columns, and it is pronounced as 3 by 2 matrix. Though we write it as multiplication, the reading is generally done as a 3 by 2 matrix. So number of rows by number of columns. And if we try to link the vectors, the chapter of vectors which we have done earlier, vector which is an ijk notation or a simple matrix notation, we said we will write a vector more like this, which is nothing but, this is also a matrix, but the only thing is this vector, for a vector the number of columns is always equal to 1. So it's a special case of a matrix where the number of columns is always 1. That is what we call as a vector. So vectors are special cases of matrices. And one few more things we need to be comfortable as far as this exam is concerned is the different types of matrices. We call something as a square matrix when the number of rows is same as the number of columns. So probably a 2 by 2 matrix. Number of rows is 2, number of columns is 2. Some A, B, C, D. This is a square matrix where number of columns is same as the number of rows. 2 by 2 matrix, 3 by 3 matrix. They all get classified as square matrices. Another important classification of the matrix is a zero matrix. All the elements inside that matrix should be zeros itself. Those kind of matrices are called as zero matrices. It could be of the size 1 by 1, 2 by 2, 2 by 3, whatever may be the size of it. It need not be a square matrix. When all the elements of that matrix are 0, then we call it as a square zero matrix. Then we also have another type of special type of matrix called diagonal matrix. What is this diagonal matrix? In a matrix, let's say I am trying to put a matrix of this form. A matrix of this form. This from the top left corner to the bottom right corner, we call that as the main diagonal or the principal diagonal of the matrix. So when all the elements of the matrix except the ones on the main diagonal are zeros, which means on the main diagonal they are all non-zeros and rest all are zeros, we call that kind of a matrix as a diagonal matrix. These are some of the terms we need to be comfortable with. All the elements on the principal diagonal of a matrix are non-zeros, whereas all the other elements which are not on the main diagonal, they are all zeros. These kind of matrices are typically called as diagonal matrices. And what we see is matrices have lots and lots of applications in the world of finance, in portfolio management. They can be used to solve simultaneous equations, and also from that standpoint it is very much advised that we understand some of the basic calculations as well as the basic aspects and definitions pertaining to the world of matrices. So with that, let's move further to look at some of the basic calculations. The first thing that comes about when we talk about a matrix is the transpose of the matrix. What is meant by transpose? It's nothing but interchanging the rows and the columns of the matrix. Now let's say you have a matrix like this: 1, 2, 3, 4, 5, 6. What is the size of this matrix? First of all, 2 rows and 3 columns. So the size of the matrix is a 2 by 3 matrix. But when you transpose it, all you are doing is tilting it. So the first column will become the first row. The second column will become the second row. The third column will become the third row. So what is happening is the rows are becoming columns and columns are becoming rows, which means a 2 by 3 matrix is actually becoming a 3 by 2 matrix. This is what is called as a transpose. So any m by n matrix typically gets transformed into n by m matrix when we are doing a transposing of a matrix. And when I transpose, the shape of the matrix is changing, the contents are changing, everything is changing. But even after I transpose, if the content does not change, that is what we call as the symmetric matrix. For example, you just see like this, any matrix like this, you do a transpose of this matrix, interchange the rows into columns and columns into rows, you will find that the new matrix is also exactly same as the old matrix, not just in the size but even in the content. Because you see, in the transposer matrix, this will become the first row, which is same as the original matrix. This will be the second row, which is same as the original matrix. So that kind of matrices are called as symmetric matrix. Then the next thing we need to be comfortable with is the basic calculations involved with the matrices. So we can start off with one simple example and do a few calculations on it. So let me take a 2 by 3 matrix. 1, 2, 3, 4, 5, 6. This is one 2 by 3 matrix. And another 2 by 3 matrix for me becomes, let's say, 6, 5, 4, 3, 2, 1. Let me tell you a few things. If I have to add or subtract two matrices, the rule is both of them should be of the same size. Both of them should be of the type m by n. This cannot be a 3 by 1 matrix and this cannot be a 3 by 2 matrix. Then I cannot add these two matrices. Please be careful about it. The size of both the matrices should be the same. If at all I have to add or subtract two matrices. So once I want to add the two matrices, the process is very simple. Positional addition. The first element of this you add with the first element of this. So position wise you just do a simple addition. 7, 7, 7, 7, 7, 7. This is what is the summation matrix. Same thing can happen if I want to take a subtraction. Position wise subtraction. 1 minus 6 minus 5. 2 minus 5 minus 3. 3 minus 4 minus 1. 4 minus 3 1. 5 minus 2 3. 6 minus 1 5. This is my subtracted matrix. So matrix addition and subtraction is very simple exercise. And as I said, it is possible only when both the matrices are of the same size. Then one more thing we have to be comfortable with is multiplying the matrix by a scalar. So let's say this is the matrix. I want to multiply it by 3. It is nothing but all the elements of the matrix will get multiplied by 3 directly. 3 4s 12, 3 5s 15, 3 6 8. This is the same thing we have done even in our vectors. So, because vector is a special case of the matrix, all all things which we have done in vectors more or less work the same way in the matrices also, or probably it should be the reverse. All the things that work in our matrices should be applicable directly to vectors. So the addition, subtraction and the multiplication by a scalar, they remain the same whether it is in vectors or in your matrices. So these are some of the things you have to be comfortable with. Then the next thing that becomes very important for us is multiplication of the two matrices. When I multiply two matrices, again there is a rule. For addition and subtraction, the rule or the eligibility criteria is both of them should be of the same size. But that is not the case with multiplication of the two matrices. The multiplication of the two matrices is possible only when the number of columns of the first matrix is same as the number of rows of the second matrix. So both the matrices need not be of the same size. Let's say if the first matrix is of the size m by n, the second if it is of the size m by n, let's say, then the number of columns of the first matrix should be the same as number of rows of the second matrix. Here this is not the case. So the multiplication is literally not possible for these kind of matrices. It is possible only when the first matrix is of the size m by n. Probably the second matrix is of the size some other n by p. Only n is required to be matched. Right? This p can be same as m, different from m. We are least bothered about all these things. Only this, the number of columns of the first matrix should be the same as number of rows of the second matrix. That is what is the eligibility criteria to multiply any two matrices. Right? We are not bothered about whether m is same as n or different from n, p is same as m. We are not bothered. Anything can be multiplied as long as this criteria is met. Now let's take one example and try to do how a multiplication can be done. For simplicity purpose, I'll take a 2 by 2 matrix, but it can be extended to any 1, 2, 3, 4, 5, 6, 7, 8. Let's say I want to multiply these two matrices. For the first matrix, you focus on the rows. The second matrix, you focus on the columns. So what you do is, first row, multiply with the first column. Then first row, multiply with the second column. So each row, multiply with each column and write in the corresponding location. And before that, if your first matrix is an m by n matrix, the second is an n by p matrix, the eligibility criteria is met, as we have already discussed. Now the resulting matrix will be an m by p matrix, which is the leftovers. The resulting matrix is a m by p matrix. It will have m rows and p columns. Okay, now how are we doing the multiplication here? The first row you multiply with the first column. So 1 and 1. So the answer will be in the first position. First row, first element with the first element. 1 into 5, 5. 2 into 7, 14. 5 plus 14 is 19. So this will be the first element of the matrix. Then first row multiply with the second column. 1 into 6, 6. 2 into 8, 16. 6 plus 16, 22. First row, second column. So 1, 2 position. First row, second column. This is 22. Now, second row, first column. 3 5s 15, 4 7s 28. 28 plus 15, 43. Second row, first column, you'll have the value as 43. Second row, second column, 3 6 18, 4 8 32. 32 plus 18, 50. Second row, second column. This is the multiplication of two matrices. When I multiply the two matrices, the value that I am going to get is 19, 22, 43 and 50. And the funny thing here, or the most important thing here, now I have multiplied this matrix with this matrix, right? Let me do the reverse. Let's say I multiply 5, 6, 7, 8 with 1, 2, 3, 4. Right? In normal multiplication, 3 into 4 equal to 12. 4 into 3 is also equal to 12. Even if I change the order of multiplication, the answer is not going to differ. But here, I clearly see that my answer is going to differ. Let's see here, first row, first column. 5 into 1, 5, 6 into 3, 18. 18 plus 5, 23 is the first value. First row, second column, 5 into 2, 10, 6 4s 24. 24 plus 10, 34. Alright. Second row, first column, 7 and 8 3s 24. 31 is the value here. Then again, 7, 8, first, second row, second column, 7 2s 14, 8 4s 32. 32 plus 14, 46. You see, all four values are different. So this matrix is not the same as this matrix. So that is what we mean by the matrix multiplication is not commutative. A simple multiplication is always commutative. Whether I do 3 into 4 or 4 into 3, the answer is not going to differ. But you can't do the same thing in case of matrices. AB need not be the same as BA. That's one more thing you have to be comfortable with as far as your exam is concerned. Then, identity matrix is one such matrix where it is more like this. All your diagonal values it's a diagonal matrix. We have discussed the diagonal matrix, right? Only the elements in the principal diagonal are non-zeros. Rest all are zeros. And a special case of the diagonal matrix where all the elements of the principal diagonal are only 1 and nothing else. Where all the elements in the principal diagonal are only 1 and nothing else, we call that as an identity matrix. Right? So 1 0 0 1, or even in case of a 3 by 3, the identity matrix is nothing but 1 0 0 0 1 0 0 0 1. Only the ones on the principal diagonal, they are all ones and rest all are zeros. That is what is called as a identity matrix. And why do we talk about the identity matrix? Any matrix multiplied with an identity matrix. Let's say a matrix. I multiply it with an identity matrix. The matrix will still remain the same. The matrix is not going to change. Whether I multiply it before or after, it hardly matters. Any identity matrix multiplied with any matrix, it will still result in the matrix remaining the same. That is the reason we call as the identity matrix. So this is one important aspect. Any matrix can be multiplied. A 2 by 3 can be multiplied with a 3 by 2. Right? Let's see one more example. I take a 2 by 3 matrix. I multiply it with a 3 by 2 matrix. Right? So this is a 2 by 3. This is a 3 by, this is a 3 by 2, 3 rows, 2 columns. This is a 2 by 3, 2 rows, 3 columns. So my resulting matrix will be a 3 by 3 matrix. First of all, the rule is satisfied. Number of columns of this is equal to number of rows of this. So the final matrix will be of a 3 by 3 matrix. Now, which is completely different from the existing two matrices. How do I get it? First row, multiply it with the first column. 1 into 1, 1, 2 into 4, 8. 8 plus 1, 9. First row, second column. 1 into 2, 2, 2 into 5, 10. 10 plus 2, 12. 1 into first row, third column. 1 into 3, 2 into 6. 12 plus 3, 15. Now, second row, first column. 3, 4, 1, 4. 3 into 1, 3. 4 into 4, 16. 3 plus 16, 19. Second row, second column. 3 into 2, 6. 4 into 5, 20. 26. Second row, third column. 3 into 3, 9. 4 into 6, 24. 33. Now similarly, third row, first column. 5 into 1, 5. 6 fours, 24. 24 plus 5, 29. Second row, third row, second column. 5 into 2, 10. 6 into 5, 30. 30 plus 10, 40. Third row, third column. 5 into 3, 15. 6 into 6, 36. 36 plus 15, 51. So this happens to be our resultant matrix. So you have to be comfortable with the multiplication of the two matrices. It is only possible when the number of columns of the first one is equal to the number of rows of the second. The resulting matrix is always the number of rows of the first multiplied by the number of columns of the second. Every row of the first matrix you multiply with the corresponding column of the second matrix and then add them up and represent them at that respective position. And now moving further, the next topic which you have to be comfortable with is finding the determinant of a matrix. Okay, and the determinant is a single scalar value and it is applicable only for a square matrix, number of rows equal to number of columns. How do I calculate it? We'll see. Sometimes people use the word determinant of A. A modulus is also representing a determinant of A, or a Greek symbol delta also represents the determinant of A. Now, depending on whether we are talking of a 2 by 2 matrix or a 3 by 2 matrix, the determinant calculation differs. For a 2 by 2 matrix, it is nothing but the product of the elements on the principal diagonal, 1 into 4, 4, minus the product on the other diagonal, 3 into 2, 6. So the determinant of this matrix is minus 2. It's one single unit per a matrix. When I say determinant of a matrix, it is nothing but 4 minus 6 in this case, which is minus 2. It can be a negative, it can be a 0, it can be a positive. When the determinant is 0, if this determinant A, the principal diagonal multiplication minus the other diagonal multiplication, if the determinant comes to be 0, we call that matrix as a singular matrix. We'll discuss why we have to talk about the singular matrix slightly in the next slide. But any matrix whose determinant comes out to be 0, we call that kind of a matrix as a singular matrix. Alright. Then, how do I find out in case of a 3 by 3 matrix? It's just not the principal diagonal and the other diagonal. There are so many other elements in that. So that's where we will break it up slightly. And we will take an example that will give you an easier way. Though the process is marked here, I think it would be easy for you to understand the computation of the determinant through the example. The first step that is done is look at the first row. In the first row, make the middle element minus. That's the first thing. Make the middle element, second element, change the sign of that. Whatever it is, change the sign of that. Then, so you take the three calculations, 1, minus 2, 3. These are the first three elements, first row. So take the first row as it is, with just the second element, the sign being changed. Now, if I am taking the 1, which is the first row, first column, eliminate this row and this column. Whatever is left, take the determinant of that. Now this becomes a 2 by 2 matrix. Take the determinant of that. 5 nines 45, principal diagonal, minus 8 6 48. 45 minus 48, make it as minus 3. I hope you are getting this. Now look at the second one. Take out the row and the column corresponding to it. You are still again left with another 2 by 2 matrix. Take the determinant of that. 4 nines 36 minus 7 6 42. 36 minus 42 giving me minus 6. Similarly, for 3, this take out the row, take out the column which it is associated with. For the remaining, 4 8 32 minus 7 5 35. 32 minus 35 minus 3. So here it is simply becoming 1 into minus 3 plus 12 minus 9. Yeah, it is becoming 0. Here the determinant is becoming 0. This kind of a matrix is called as a singular matrix, where you find the so if forget about the singularity for right now, the simple way you find out the determinant in case of a 3 by 3 matrix is the first row. Take the three numbers separately, put a negative value to the middle one, or change the sign of the middle one. Now for each of them, remove the row and the column to which it corresponds to. Then it becomes a 2 by 2 matrix. Find the determinant of the 2 by 2 matrix using the process which we have discussed above. The main diagonal, principal diagonal product minus the other diagonal product. So multiply it with that particular value and then add it up. Whatever is the number that comes out finally, that is your resultant determinant. If that determinant is 0, we call that matrix to be a singular matrix. That's again a terminology that we are talking of. Any matrix whose determinant is 0, we call it as a singular matrix. I hope this is comfortable for you, because computation of the determinant is one of the important aspects in matrix calculations. Then, once we are comfortable computing the determinant, the next thing we should be comfortable with is computing the inverse of a matrix. A particular matrix, when I multiply with my required matrix, it should result in an identity matrix. That is what we call as the inverse matrix. Any matrix with which I multiply the existing matrix, which will result in an identity matrix. This is what we are saying. Any particular matrix, this is the new matrix. If let's say A is the current matrix which I am interested in. For this, if I want to find out the inverse, it is nothing but if I multiply with that particular matrix, it should result in an identity matrix for me. So in case of 2 by 2 matrix, the process is very simple. 1, 2, 3, 4. If I want to find out the inverse of this particular matrix, the process is simple. First step, find the determinant, which we have already found out earlier. Find the determinant. In this case, the principal diagonal multiplication minus the other diagonal multiplication. 4 minus 6 minus 2. Then the second step is create a matrix which is the principal diagonal, just reverse the positions. 4 and 1. On the principal diagonal, reverse the positions. Fair enough. On the other two, reverse the sign. Change the sign. Don't reverse their positions. Only change their signs. On the principal diagonal, reverse the positions. On the other diagonal, just change the signs. This is the new matrix and make it like 1 by the determinant. Make it 1 by the determinant. So which means the new matrix is 4 by minus 2, which is minus 2. Minus 2 by minus 2, which is 1. Minus 3 by minus 2, 1.5. 1 by minus 2, minus 0.5. This is the resulting matrix, inverse matrix. Just to check out, which means if this is A inverse, this is A. If I try multiplying A with A inverse, 1, 2, 3, 4, I multiply it with minus 2, 1, 1.5, minus 0.5. I should get identity matrix. Let's see. First row multiplied with first column. 1 into minus 2. Minus 2 plus 2 into 1.5. 3. 3 minus 2. 1. Very good. 1 into first row multiply with second column. 1 into 1. 1 plus 2 into minus 0.5. Minus 1. 0. 3 into minus 2. Minus 6 plus 4 into 1.5 plus 6. 0. 3 into 1. 3. 4 into minus 0.5. 2. Minus 2. 3 minus 2 is 1, which is coming out to be an identity matrix. So for a 2 by 2 matrix, finding out the inverse is a straightforward task, wherein first step is you find out the determinant. The second step is along the principal diagonal you reverse the positions, whereas the other elements you just change their sign. That is what will become the inverse of a matrix for a 2 by 2. And as I said, if the matrix is having a determinant 0, obviously 1 by determinant will make it not defined. So the inverse of the matrix does not exist for a singular matrix. Inverse does not exist for a singular matrix. Now, if at all the question comes out in terms of determining the inverse of a 3 by 3 matrix. A 2 by 2 matrix is fair enough, straightforward. But if it is a 3 by 3 matrix, it's a slightly lengthier procedure. Right? So let's try out that procedure also, because I don't think that kind of question may come up for us in the exam, but in case it comes up also, we should be prepared for it. So that's where I'm taking up 1, 2. Oh, okay. This because 1, 2, 3, 4, 5, 6 is a singular matrix. The inverse will not exist for that. Okay. So let me take 3, 1, 2, 2, 3, 1. Okay. So let me take this matrix. So for this, the first step again lies the determinant. So 1 into 1 minus 6 minus 5. For the second number, I have to change the sign. Minus 2 into, if I remove the row and the column, 3 minus 4 minus 1, plus the third number, I change the row, column, 9 minus 2, 7. So at least the determinant is existing in this case. 1 into minus 5 plus 2 minus 3 plus 21. 18 is the determinant in this case. So the first step is still finding out the determinant. The second step is find out the cofactors. Okay, this is a slightly tricky part. Okay, find out the cofactors and put them in the transposed positions. What do I mean by the cofactor here? For the first one, You remove the first row, first column. First row, first column. So I am left only with this box. Find out its determinant and write it in a matrix. 1 minus 6 minus 5. Write it here. Similarly, for the second, remove the row, remove the column. 3, so it becomes a small matrix, 3, 2, 2, 1. Find the determinant of this. 3 minus 2, or 3 minus 4, minus 1. Alternatively, change the signs. So, because I got 3 minus 4, minus 1, take it as plus 1. Write it in the transposed location. So for the first one, you don't change the sign. Second one, you change the sign. Third, don't change the sign. Fourth, change the sign. That's how. Now let's say if I want to go with the third one, remove the row, remove the column. So this is the one. 3, 1, 2, 3. So try to find out 3, 3 is 9 minus 2, 7. So I don't need to change the sign for it. So write it as 7. Then similarly, fourth, remove the row, remove the column. It makes 2, 3, 3, 1. So 2 minus 9 minus 7. I need to change the sign now. So write it as 7. Then for this middle one, remove the row, remove the column. 1 minus 6, which is minus 5. I write the minus 5 here. I don't need to change the sign. For again the next one, let's say this one. Remove the row, remove the column. 3 minus 4 minus 1. I need to change the sign. Write it as plus 1. Similarly, row, column. 4 minus 3, 1. Write it as 1. For this, remove the row, remove the column. 2 minus 9 minus 7. Need to change the sign. Make it as 7. Only for these values, change the signs. Finally, this one. 1 minus 6, which is minus 5. Keep it as it is. So this is what is called as my adjoint matrix. What is this adjoint matrix? A matrix for which you are trying to find out the cofactors for each of the elements and then transposing those cofactors. Cofactor is what? For each of the element, you remove the row and remove the column corresponding to it. So it results in another 2 by 2 matrix. Find the determinant of that 2 by 2 matrix. So the list of all those determinants is what is my cofactors. With alternate signs for the, changing the signs for the alternate values. And after that, I change their positions. I transpose their positions to get a new matrix. That matrix is what is called as the adjoint matrix. And I just divide this by 1 by the determinant. That is what will give me my inverse. So in case of this matrix, the inverse is nothing but 1 by 18 multiplied by minus 5, 7, 1, 1, minus 5, 7, 7, 1, minus 5. You try multiplying this with the original matrix just to see this. 1, 2, 3, 3, 1, 2, 2, 3, 1. Just try multiplying them. First row with the first column. Minus 5 plus 7 into 3, 21. Minus 5 plus 21, 16. Plus 2, 18 divided by 18 makes it 1. First row, second column. Minus 5 into 2, minus 10. Plus 7 plus 3, 0. First row, third column. Minus 15 plus 14 plus 1, 0. Second row, first column. 1 minus 15 minus 14 plus 14, 0. Second row, second column. 1 into 2, 2. minus 5, minus 3 plus 21, 18 divided by 18, 1. So like that you will definitely get something like this, which means this matrix is what we are calling as the inverse of the original matrix. So you need to be comfortable in trying to determine the inverse of a matrix given the original matrix. Generally, most of the questions may be pertaining to a 2 by 2 itself, but in case a 3 by 3 is given and you may have to find out the inverse, this is the process that is typically followed for it. So I hope you are getting some level of comfort in terms of finding out the inverse of the matrix. All right. Now let's move further. The other scenario, the other examples that you need to be comfortable with is finding out solving the simultaneous equations. Let's say these three equations are given to us. How do I solve? How do I solve the values of x, y, z? Probably I can use the simultaneous equations method which we have discussed in algebra, and I can solve them. But using matrices, how do I solve them? Okay. So first thing, write the coefficients in the form of a matrix. X plus 2y minus z. So 1, 2, minus 1. 2, minus 3, 2. Third equation, 3, 1, minus 3. So this is the original matrix. Write it as into x, y, z. So if you try multiplying it, it is nothing but x plus 2y minus z. So equate it as minus 4, 1, minus 17. Now, okay, what you can do is, let's say if you multiply with A inverse, think of something as the inverse of this. Think of something as the inverse of this. So you are multiplying it with A inverse here. Here also you multiply it with A inverse, this side. So A inverse into this. Now obviously you know that A into A inverse is nothing but I into x, y, z. So here this becomes I into x, y, z, and here this becomes A inverse into minus 4, 1, minus 17. This is what will help me in finding out I into xyz is nothing but xyz. So using that I can find out the value of x, y and z. So let's try doing that, right? So for the first thing, first find out the inverse for this. How do I find the inverse for this? First step is determinant. 1 into minus 3 into minus 3, 9, minus 2, 7. All right. Minus 2 into, we have to change the sign for the second one. So minus 2 into, remove the corresponding row and the column. 2 into 3, 6. Minus 3 into 2, 6. So 0. Minus 1. I am not changing the sign for the third one. Remove the row, column. First row, first column. 2 minus of minus 9. So 11. So 7 minus 11. So the determinant is becoming minus 4. All right, that's the first. Then we are talking about the inverse, which is the second step, wherein, okay, I'll do it as 1 by minus 4 into, I'll write the cofactors, okay, for the first one, 9, oh sorry, for the second, this was not, so here, this was minus 3. So minus 6, minus 6. This was minus 12 in fact. So we got it as plus 24. 7 plus 24. 31 minus 11. So this becomes 20. whatever it is. So you please focus on the process. 1 by 20. Okay, for the first one, 9 minus 2, 7. For the second, I have to change the sign, but before that, remove the first row and the second column. 2 into minus 3, minus 6, minus 6, minus 12. Change the sign of that, make it 12. And put it in its transposed location. So this is 12. Then for the third, 2 minus of minus 9, which makes it 2 plus 9, which is 11. Take it like this. Then for the second row, first column, 2 into minus 3, minus 6 plus 1, minus 5. And take the change of sign, so make it 5. And then what about the second row, second column, minus 3 minus of minus 3, which is plus 3. Minus 3 plus 3, making it 0. And then second row, third column. Similarly, I remove the row and the column. 1 minus 6 minus 5, change the sign of it, make it 5. Then third row, first column, 2 minus 3, 4 minus 3, 1. Take it as it is, don't change the sign. Second, 2 minus of minus 2, make it 4. And okay, 2 minus of minus 2, 4, and I have to change the sign, make it minus 4. And what about the last? Minus 3 minus 4, make it minus 7. So this is the inverse. What is the inverse now? 1 by 20. Probably if I had done all the calculation right, it is 751, 12, 0 minus 4. So this for the second. So alternate, you make sure that whether you have a minus 6 plus 1 minus 5, you have done that. Here also 1 minus 6 minus 5. Okay. And what about this? 11, 5 minus 7. Okay, let's try it out. So this is the inverse. And this I am multiplying with minus 4, 1, 17. Now the first row, 7 into minus 4, minus 28 plus 5, minus 23 plus 17. Minus 17. This is minus 23 minus 17, which comes minus 40. Minus 40 by 20 is minus 2. So the first value is minus 2. Second, 12 into minus 4, minus 48, and plus 68, 20. 20 by 20 is 1. And what about the third? 11 into minus 4, minus 44, plus 5, minus 39, minus 39, minus 189. Sorry, minus 119. Minus 39 plus 119, that works out 2. Minus 39 plus 119 is 80. 80 by 20 is 4. So I am getting x, y, z as minus 2, 1, 4, which means x equal to minus 2, y equal to 1, and z equal to 4. Just substitute it back to check it out. Minus 2 plus 2 minus 4 equal to minus 4. And you will get your values. So this is one mechanism of solving your simultaneous equation using the matrix method. So simple logic is, you find out the simplified way is, if you have A, B, C given, 1, 2, minus 1, 2, minus 3, 2, 3, 1, minus 3. If this is your A, find out A inverse directly and multiply this A inverse, whatever the matrix you got, with the output matrix. Whatever the values you get will be your values of x, y and z. That is using the inverse mechanism. Of course, you can use the other mechanism also, but as far as our calculations are concerned, we need to just know the answer for it. So that is where we will go with the matrix transformation inverse calculation method to find out the to solve the simultaneous equations also. There is one more method called transformations method. But yeah, at the end, because this is a multiple choice kind of an exam, we are more bothered about finding out the values of x, y, z. So whatever the inverse is a straightforward mechanism. So we can use the inverse mechanism to actually calculate, solve the values of x, y and z in this case. Then one more concept which we have to understand as far as this subject is concerned, this chapter is concerned, is the concept of eigenvalues and eigenvectors. This is nothing but any vector or any particular vector that makes for this particular A. If I want to find out the eigenvalue, it is nothing but any particular value of lambda that makes A minus lambda I a zero matrix. Whatever this value of lambdas that makes the A zero matrix, transforming this A by multiplying it with by subtracting a lambda I from it, whatever that matrix that makes A as a zero matrix is what we call as the eigenvalues. So the simple logic, I think it is better understood using the example. I take this example, 1, 2, 3 minus 4. If I subtract lambda I, so I need to find out that particular lambda which makes this particular matrix, or probably which makes the determinant of this particular matrix 0, not a zero matrix. The determinant of this particular matrix 0, which means makes it as a singular matrix, is what we call as the eigenvalues. Now how do I solve for it? I can take it like this: 1 minus lambda, 2, 3, minus 4 minus lambda. This is what is my new matrix. Find out the determinant for this matrix. So values on the principal diagonal minus the non-principal diagonal product is equal to 0. Multiply it. 1 into minus 4, minus lambda plus 4 lambda gives me plus 3 lambda, plus lambda square minus 6 equal to 0. So making it lambda square plus 3 lambda minus 10 equal to 0. So that makes lambda plus 5. You can use your quadratic equations method to find out the lambda is equal to 0, making it lambda equal to 2 or lambda equal to minus 5. So here the values 2 and minus 5, these are the ones that are making the determinant 0 or a singular matrix. A is becoming a singular matrix if I subtract lambda I, where lambda equal to 2 or lambda equal to minus 5. So the eigenvalues for this particular matrix, which we have taken up, the eigenvalues are 2 and minus 5. So you are typically asked in most of the question, find the eigenvalues of this particular matrix. It is nothing but from the matrix you subtract lambda I, and the resulting matrix take the determinant, equate it to 0. Whatever the value of lambda that makes the determinant equal to 0, Those are all the eigenvalues of that particular matrix. Now, in this example, we came to know that 2 and minus 5 are the eigenvalues of this matrix. Okay. So, let's start with 2. If lambda equal to 2, what is the matrix becoming? 1 minus lambda, which is minus 1, 1 minus 2. This is 2. This is 3. Minus 4 minus lambda. Minus 4 minus lambda is minus 4 minus 2 minus 6. This is it. This is your resulting matrix into xy is equal to 0, 0. So how do you get it? Minus x plus 2y equal to 0. Or the second one is coming out to 3x minus 6y equal to 0. So it is coming out as x equal to 2y. So how do I write it in the matrix form, in the vector form? 2, 1. X equal to 2y. So double. So anything times, so I'll write it as a k, 2 and 1. So probably a 2 and 1 multiplied by some scalar, because in all those cases x is always equal to 2y. Because both the equation 3x equal to 6y, which means x is equal to 2y. So any vector of the form 2, 1, where x is double that of y, is an eigenvector for this particular matrix. The eigenvector for this matrix is 2, 1. All the series, probably 4, 2, 6, 3, that is where we have put k. K is any scalar quantity. So these are all the possible eigenvectors for this matrix. Similarly, if I assume that my lambda equal to minus 5, what is coming out here? 1 minus lambda, which is minus 4, 2, 3, minus 4 minus lambda, minus 9. This is the resulting matrix into xy is equal to 0, 0. Which is again becoming minus 4x plus 2y is equal to 0. Oh, 1 minus lambda, 1 minus minus 5. This is becoming 6 actually, it's not minus 4. So the equation is coming out as 6x plus 2y equal to 0, or 3x minus 4 minus how minus 5. So this is becoming plus 1. 3x plus y equal to 0. Again, both of them are working out to be the same. So 3x plus y equal to 0, which means y equal to minus 3x. Right? Y equal to minus 3x. So how do I write it in the matrix form? If this is x, x is 1, y equal to minus 3. So any k multiplied by 1 minus 3. So the vector for this case, when lambda equal to minus 5 is 1 minus 3. The vector for this is 2, 1. So any of those vectors of the form 2, 1 and 1 minus 3 are all called the eigenvectors of this particular matrix. So any matrix given, I should be comfortable finding out the eigenvalues as well as the eigenvectors. Eigenvalues are scalar quantities, the values of lambda. Eigenvectors are a series of vectors whose I and j coefficients are determined by substituting the lambdas back into the equation and equating that to zeros. These are some of the basic calculations you should be comfortable with using the matrices. There are 6 to 7 different areas we have covered, right from the basic addition, subtractions, multiplication by a scalar, multiplication of the two matrices, finding out the determinant of the matrix, finding out the inverse of the matrix, using matrices to solve simultaneous equations, and also the concept of eigenvalues and eigenvectors. I hope you are comfortable solving all these kind of calculations. If you have any further queries, you can give me a call on the number that is mentioned below, 9848012123. You can also send me an email on vamsidhar@pacegurus.com and I can respond back to your doubts. And you can visit my website www.pacegurus.com for updates regarding the trainings, consultings, and corporate trainings we do in the areas of finance, investments, statistics, analytics, and actuarial sciences using tools like Excel, VBA, and SPSS. I hope this session gave you a decent insight into the world of matrices. Thanks a lot for listening to this session. Thank you very much.